Okay, so good afternoon, and this is the second of the introductory lectures to Emergent States of Matter. So I'm going to start off by talking about the onset of emergence, and the onset of emergence is associated with phase transitions. So I want to talk a little bit about those, but this isn't a class on phase transitions, and so we're going to see particularly what it is that differentiates emergent states of matter from a course on phase transitions. So let's just quickly remind ourselves what happens in phase transitions. So in phase transitions, you might be having something like a liquid-gas transition. And so here we have the phase diagram of regular matter. Here's pressure, here's temperature. This is the phase diagram. This is the solid phase, which is when you get at low temperatures and high pressures. At high temperatures and low pressure, you get a gas phase, and then in between, you get the liquid phase. And then what we're particularly interested in phase transitions is we're trying to understand either the transition between liquid and solid, or say here, the transition between liquid and gas. This line here between solids and liquids is a first order transition. So there's entropy generation and latent heat at that transition. This transition between liquid and gas is a first order transition as well, but the order parameter for this transition is the density difference between the liquid, which is more dense, and the gas, which is less dense. And that density difference gets smaller and smaller as you go closer to this critical point, and at this critical point it disappears. And beyond this critical point, there really is no distinction between a liquid and a gas. And so the critical point in this particular case is actually just the vanishing of a line of first order transitions in the pressure temperature plane. Okay, and so this is what you would see. Here is the meniscus. The size of the meniscus is controlled by the correlation length. And as you go towards the critical point, that diverges, and then eventually you get into a phase where you can truthfully say the distinction between gas and liquid doesn't exist, and you only have a fluid. So what that means in particular is that you can do the following thing. If I take a liquid at some particular pressure, and then I heat it up, so I'm going along this line here as I've just drawn it, what would happen is I heat it up, I would get to this point where there is liquid-gas coexistence, and that's what you can see over here. The meniscus is showing you there is coexistence. You will sit there and sit there and sit there until you get to a higher temperature, and then you'll start going up like this. So so that sequence of events happens at this coexistence point. I can go from liquid to gas without going through a phase transition. So I can start off. I can start off here. I'm usually thinking of this in the other way around, so I'm slightly confused. So if I start off with a liquid, I increase the pressure, so I go up to here. I increase the temperature, so I go up to here, and then I decrease the pressure, so I go down to here. I can go to liquid and gas without going through this first order phase transition without ever seeing a meniscus. So thinking of liquid and gas as being distinct phases is a little bit misleading, because in a phase diagram, they're not topologically distinct, unlike, say, solid and liquid, which are topologically distinct. And by topologically distinct, what I mean is that I cannot go from liquid to solid without going through some kind of phase transition. Usually it's a first order transition, but in some disordered solids, it can be a second order transition. But there always has to be something between these phases, some kind of non-analyticity. And the reason for that is that they have different symmetry. And the symmetry cannot emerge in a gradual way. It is either there or it isn't. And so if it's broken or not broken, that tells you something about the phases of matter. And so this symmetry is the way that we're going to be thinking about emergent states of matter in this course. We're going to be thinking about it as being associated primarily to changes in symmetry. Now, that is a perspective that we have in this course. It's a perspective that is not the only perspective to thinking about emergent states of matter. So,
can I ask a question before you move on?
Yes, sure, Mark.
First, there was something in the chat about turning on captioning,
Oh,
um,
yes, that's
but
right.
I wanted to know. Can you explain more in detail what you meant when you said it's topologically distinct? Nothing in your explanation after you said that sounded topological to me.
Yeah. Okay, I've switched on captioning, and so you should be able to see that. And let me hide the meeting controls. Where is that? There. Okay, so you can see the caption, so everybody's happy with that. Now, what I meant by topologically distinct is this. I meant that I can go from liquid to gas without going through any transition. The transition is a line of singularities. So I think of these as being topologically connected.
Oh, so you're talking about the topology of this chart, I guess.
Yes, I'm talking about the
Okay.
topology of the phase diagram, not
Okay.
not the topology of the excitations of the system.
Okay. Great. Thank you.
So that's an important distinction. Thanks for the question. Yeah. But that brings me on to what I want to talk about. So the viewpoint that has emerged in condensed matter physics over the last 20, 30 years has also been the discovery that you can have states of matter that have the same symmetry, but have very different topological order. And so if I were to say, if I were to make emergent states of matter 1, emergent states of matter 2, emergent states of matter 1 would be on symmetry breaking, emergent states of matter 2 would be on topological order. So we may talk a little bit about topological order later in the course if we feel like it. But what I will be talking about is the point that even if you have just spontaneous symmetry breaking as the way of thinking about emergent states of matter, nevertheless there are topological excitations, and those are going to be very important. So when we actually get to the first homework set of the class, for example, we're going to be trying to understand. The first things you'll be asked to do is try to understand something about the topological excitations of different symmetric states of matter. Okay, so let's just talk very quickly about critical points. I don't want to say too much about this. I'm assuming that most of you have been to my 504 StatNet class, so you know that near a critical point you have large fluctuations. So this is an Ising model simulation where you can think of it as being a liquid gas or an Ising model. So black would be regions of high density, white would be regions of low density if you're thinking about a fluid, or black would just be spin up and white would be spin down. And then what you're seeing is as you vary the temperature, you can see the size of the domains grows. And in particular, what you're supposed to see from this is that the size of domains grows as you get towards TC, but also that when you're close to the critical point, what you see are domains on all scales. And that's not really easy to see from this picture here. But if you look at the black regions in this predominantly white background, you'll see that there's domains of size, well, almost as big as this picture, and then there's domains on all scales all the way down to the smallest ones. Whereas if you look at this picture here, where you're well below the critical point, 0.98, you can see it's mostly white with just a few patches of black. And those patches of black just have a very characteristic size, which is the correlation length. And so the idea is that when you're near a critical point, you have large fluctuations, you have fluctuations on all scales. And what that means is that when I look at correlations, they are not characterized by a single scale, they're characterized by all scales. In other words, there's no scale at all. And so what that means is that you expect that correlations decay exponentially when you are away from a critical point and decay as a power law at the critical point. Now, there's a lot of extra things to say about that, but I don't want to go into that in this particular course, at least not right now. Okay, so when we talk about emergence, what we're thinking about is that there's two regimes. So this is, say, a magnet. So this is high temperature. This is the magnetization. As I go below the critical point, what I start to see emergent is the magnetic order. And the topic of phase transitions in the normalization group course is to understand the asymptotic behavior asymptotically close to this temperature Tc, and in fact to understand what is the analytic structure of, say, this curve here. What is the functional form as you go below TC, for example? And there's a whole variety of scaling laws that relate various observables such as susceptibility, response functions, magnetization, which is the order parameter, correlation functions, thermodynamics. So let's just talk very briefly about those because I want to talk about them a little bit later when we talk about emergence in non-equilibrium systems. So the picture I just showed you was this one over here, and so what you're looking at is the magnetization in zero external field as I go below TC, and what we learn is that this behavior is actually non-analytic. It's described by a power law function beta, which is not the function that you would naively have expected. So if you were to ask, I'm going to give you, 10 seconds, make for me a theory of this curve here. Okay, how would you do that? Okay, so the 10-second theory says, oh, well, let's look at this in the temperature. Maybe I should, well, let's just look at this, invert the axes, so temperature is vertical and M is horizontal. So then, what you will get is this. Let me annotate it like this. So if I were to annotate, if I were to draw it this way, so what I would have is this. Here is M, here is T. This curve looks something like this. And now what I would do is I would continue this on the other side. So this is M positive, so M negative would look like this. And then what I would say is, well, what is this curve going to be? Well, let's write this as a function. T is a function of M. And what is T as a function of M? Well, it's clearly an even function because there's no external magnetic field. So spin up and spin down are the same. So this function should be a function of M squared because it has to be an even function of M. And so therefore, the simplest possible form for this function is some T naught, that's over here, and then minus some coefficient, let's call it A, times M squared. And so then if I inverted that, then what I would get is that M is going to go like T naught minus T to the 1/2 power. So there you are, there's a 10-second theory for what the shape of this curve would be. And that sounds like an incredibly persuasive theory for what you would expect to see in a situation where you have order emerging, magnetization in this particular case. But actually, that's not what is seen. So what is actually seen is something very different. You see an exponent beta, and this exponent beta is closer to a third, at least in 3 dimensions, like 0.326 or something like that. And the whole course on phase transitions in the normalization group is to try to understand what could possibly be wrong with this argument here. So this argument is wrong because it disagrees with experiment. And the real question is why, and why it's wrong. That's what's the topic of my phase transitions in the normalization group course. Okay, so if you want to take a screenshot of that, go ahead, take a screenshot. I'm going to clear the screen in 5 seconds. 4, 3, 2, 1, gone. Okay, now let's go back to this picture over here. This shows you the external magnetic field and the temperature plane. And so what this graph corresponds to is having H equals 0 and going down from high temperatures to low temperatures. And as you go through TC, you go through this continuous phase transition. And it's called a continuous phase transition because the order parameter, the magnetization, goes continuously to 0, whereas if this was a first order transition, this would go down like this and then would jump discontinuously. Now, if I have an external field, then I do have a first order transition, and that first order transition occurs when T is less than Tc, and I go from plus H to minus H. So let's just think about this in cartoon pictures. Let's suppose I'm near 0 temperature. So then if I apply an external magnetic field, the spins will all mostly will all be pointing up. As I take the external magnetic field H and make it go from pointing up to pointing down, then what will happen is the magnetization will go from a number that's +1 to a number that's -1. And it will do that discontinuously. So if H is very small, the system will always orient upwards and the magnetization will be +1. If H is very small but negative, the system will always orient downwards and the magnetization will have magnitude -1, excuse me. So what that means is as I go across this line here, H equals 0, T less than Tc, I have a discontinuity in the magnetization. And that's true for every temperature below the critical temperature. And that discontinuity it means that there's a discontinuity in the magnetization. The magnetization is the first derivative of the free energy with respect to external magnetic field. And so therefore it's a discontinuity in the first order derivative of the free energy. And so it's a first order phase transition. Okay, so that's this phase diagram. Now, what happens at this critical point, we've seen that there's some weird non-analyticity here. Let me tell you about something else that happens. So normally, if you're anywhere in this phase diagram, and I said to you, I'm going to apply an external magnetic field to a magnet, what is the magnetization that it's going to induce? So what you would say is, well, if I apply an external magnetic field, the magnetic field that is induced, the magnetization that is induced in the material is proportional to the magnetic field that I apply. And that's makes great sense. That would be what you would expect from linear response theory. Linear response theory says the response to a perturbation is proportional to how big that perturbation is, as long as that perturbation is small enough. There may be nonlinear terms as well, but at least to first order in the perturbation strength, the response will be linear. Now, when you get close to this critical point here, right here, what you find is that that breaks down. Linear response theory breaks down. So if you sit at Tc, that means you're sitting on the critical isotherm. And if you then ask, how does the magnetization depend on H? Normally you would say M should be proportional to H, and that would be Curie's law. But at Tc, that breaks down. It goes as some weird power of H, and we conventionally write that power in terms of a critical exponent little delta as H to the power 1 over delta. Okay, so these two things happen. This is the non-analyticity and the order parameter. This is the breakdown of linear response theory, and both of these things happen in critical phenomena. Now, where the modern era of critical phenomena really took off was the observation by Widom and Kadanoff that both of these stylized facts follow from this similarity formula. So what does this similarity formula say? So little h is the external magnetic field normalized by Kb times Tc. Okay, so little h is just really the external magnetic field here. Little t is the difference between the temperature and the critical temperature, normalized by Tc. So it's a dimensionless measure of temperature. And so normally you would say, well, the magnetization should be a function of temperature and field, and you can see why just from these phase diagrams. But what happens at or near the critical point is that m is really just a function of one variable, this combination of h and t. Delta is some new critical exponent, and this function here is what's called the scaling function. So this is called a similarity formula, and it's the basis of universality. So let me show you how that works. So you would say that m should be a function of two variables, but this formula here says that if I plot m divided by t to the beta as a function of h divided by t to the delta, then that should just be one function, f of x. So that's called the scaling function. So you do that. So here is the magnetization scaled in that way. Here is the temperature scaled by the external magnetic field in that way. And you can see that all those data, which should be a function of two variables, and so should fill the plane, actually fall into one curve, one line. And these are data, in fact, from 5 different magnetic materials. And they're all quite different. And yet all these data, when plotted in this way, fall onto one universal curve. And this line through the middle here is the renormalization group prediction for what that curve should be, with no adjustable parameters. So it's a very remarkable fact that depending on the material, material properties don't really matter. They don't determine the critical exponents, and they don't determine what this curve is. And so this is the idea of universality, and it is practically, it's a big surprise how this worked. And of course, the purpose of the normalization group was to try to understand how this comes from and how to be able to understand these things. Now, why this is so important is because we're going to see it relates to emergence in a particular important way. But the thing I want to emphasize is that this success is something you shouldn't have expected. So normally you might say, well, okay, well, what's the big deal here? Somebody made a really good theory, they solved it, they calculated properly, the measurements fit the theory, there's no big deal here. But so you might say, well, what is the theory? Well, the theory is the Heisenberg model for a magnet. So it's a particular spin system, and we'll talk a bit more about that in detail later. But this isn't really a model that gives a precise prediction in agreement with experiment. This is actually a model of a model of a model of a model of a model that gives a precise prediction in agreement with experiment. Okay, and why do I say it like this? Well, at the underlying level of description, you have quantum chemistry, which is, we talked about levels of description last lecture. And so now we're really seeing where this comes from. You've got quantum chemistry at the lowest level of description. The next higher level of description of a magnetic material, you might have the electronic structure, the band structure, the electron-phonon interactions, the electron-spin interactions, spin-orbit interactions, and so on and so forth. Then you say, well, let's make a simpler model of that. Let's ignore the electronic structure, but let's just focus on the magnetic dipole moments. So we get a model of quantum spins, which is a quantum Heisenberg model, and that's too hard to solve. So let's just throw away the quantum mechanics and just make it classical, and that's too hard to solve. So then let's make a coarse grains theory of it, which is Landau theory, which is kind of what we were doing at the beginning of today's lecture when we tried to make a 10-second theory for how you fit the magnetization curve. And so, and the remarkable thing is this: each step of the way, going from this level of description to 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 this level, you are making non-systematic approximations. For example, going from quantum to classical, or electronic structure to a spin model, and so on. These are all non-systematic approximations that you can kind of say it seems reasonable, but they're not necessarily ones that you can say are systematic, and I can compute order by order in perturbation theory what are the corrections to these approximations. So you would think that normally if you make a theory which describes something in reality, and then you make approximations, as you make more and more approximations, the agreement with experiment will be reduced. And if you don't make too bad approximations, you'll be able to get reasonably good agreement with predictions. But the predictions that we make with renormalization group theory and the theory of phase transitions are incredibly precise. I mean, may not be quite as precise as, say, 10 significant figures in quantum electrodynamics, whatever it is, but close to that. We can really predict these exponents to very high accuracy and observe them and all the phenomena associated with them with very high accuracy in experiments. And so that really is remarkable, that what we're looking at in critical phenomena is something that is very resistant to all these simplifications that we've made. And that's the idea of universality, that all these different levels of description all flow to the same underlying theory, which makes the same simplest predictions. So that's what we talked about last time, about levels of description. And in critical phenomena, that is where you see it first. So now let's go back to this picture that we started with. So what I've spent the last 10 minutes or so talking about is the phenomena that accompany the critical point. And so that's what my renormalization group class is all about. What we're interested in this class is something different. And we'll talk about this in detail, but as we go below the critical point into this regime here, now what's happened is this: the magnetization fluctuations are not small. In other words, the magnitude of the magnetization is substantial. It's not infinitesimal as it is over here. So the direction, so the magnitude of the spins, the magnetization is something that is fairly fixed. But because the spins are a Heisenberg model, and they can point in any direction in space, they have directional fluctuations or phase fluctuations, as I'd rather call it. And so what's happening here is, in this regime, phase fluctuations are very important, but amplitude fluctuations of the order parameter are not important. And so what happens here is a whole suite of phenomena that are associated, which are universal in the sense that there's universal characteristics to them. And we're trying to understand now what goes on in this regime, and we'll see that that regime is dominated by a variety of generic consequences. The fact that you can have a long wavelength description of the phase order in the system. We can make certain statements about the excitation spectrum. We can make some statements about the existence of topological defects and what their dynamics and characteristics will be, all based just on symmetry and universal statements, without really having to know very much in detail about what the materials are actually made of. So it's a kind of universality that mirrors what happens here, but it's not so much a universality in terms of non-analytic behavior. It's a universality in terms of what the actual behavior of the system is on appropriate scales of time, space, and energy. And so that's what we're going to be trying to understand in this course, is the generic consequences of spontaneous symmetry breaking in systems which have continuous symmetries. So later on, when we get beyond this, we will be talking about systems with continuous symmetries as opposed to systems with discrete symmetries, so like Ising models. So let me just recapitulate what those things are. So the universal outcomes of emergence, what we're going to see is that emergence is associated with a breaking of symmetry. So in a magnet at high temperatures, the spins can point in any direction, full rotational symmetry. As you go down to low temperatures, that rotational symmetry is broken. The spins will find a configuration based on the history of the system, and they'll align along some randomly chosen direction. And so we say that there is broken rotational symmetry, and we call that spontaneous symmetry breaking. And we'll talk more about that in detail. I don't really like the term spontaneous symmetry breaking, because I think it hides something about the dynamics of phase transitions, and also it hides something about the ergodicity breaking, which also accompanies phase transitions. Those of you who took my Stat Mech class will have heard me talk about that. I don't know if I'm going to get into that so much in this course. Now, the other thing about emergent states of matter is that they have its emergent states of order. So we're looking at the order of, say, the magnetization in a magnet, or the magnetization, magnetization magnet, or maybe off-diagonal long-range order, which is something we'll talk about, quantum order in, say, a superfluid or a superconductor or something like this, some kind of order parameter which is quantum mechanical in nature. So the idea is then that you can have a state of order which is uniform throughout the system, but in systems that have continuous symmetries, you can have holes in that order. So holes in order are what we call defects. So for example, you may have a crystal. A crystal may well be a system where all the atoms are in some periodic array, and so there's an order which is just exemplified by the Bragg scattering or the X-ray diffraction, telling you that the atoms sit at lattice spacings. But of course, you can have vacancies. You can have a missing atom. And so that would be a hole in the crystalline order. So that would be called a vacancy, and that is a kind of defect. But you can have other kinds of defects that have a topology associated with them, a topological charge. And an example of that in a crystal would be a dislocation, a screw dislocation, for example, or an edge dislocation. And we'll talk a little bit about that. So the reason, how do you detect these dislocations? Well, they are breaks in the order of the system, and typically they can be understood by constructing a conserved quantity, which is constructed from a line integral of a path in space around that object. So we'll discuss that in a lot in the context of superfluids and superconductors, not so much in the context of dislocations. And if we decide later in the semester to talk about liquid crystals, we'll see that these kinds of topological defects are very important there. So that's one of the main messages, is that when you have spontaneous symmetry breaking, you will also have, from the way that the symmetry is broken, we can discuss what kinds of topological defects will be present. And why topological defects are so important is that they can dominate the large-scale properties of materials. So, for example, if you're looking at, say, crystalline materials, the mechanical response of the material is strongly dominated by the structure of the defects in the material, whether they're topological, like dislocations, or non-topological, like vacancies or grain boundaries or other things like this. So defects in states of order are very important to understand, and particularly in superconductors, particularly in gauge theories and things like this. These are really the topological sector of the theory is something that's very important. Now, the other area where we were interested in when we're looking at emergence is we're interested in looking at not just the ground state of the system, but the low energy excited states of the system. So we take our system at low temperatures, it will have some order, very low temperatures will have some order. As I raise the temperature, the system will have thermal fluctuations, and the excited states will become occupied. And so one wants to know, can one say something specific about these low energy excited states without having to solve the whole problem? And it turns out that you can, and some of you may have heard about things like Higgs bosons and Goldstone modes and things like that. So it turns out that there are generic consequences that come from symmetry considerations that tell you about the low energy excited states of the theory. And we're going to be talking a lot about that in the context of superfluids and superconductors and gauge theory. So those are some of the universal outcomes of emergence. Now, the next thing I want to talk about for the next few minutes is that this universality is really important because we can exploit it to make predictions. And we exploit it to make predictions using the idea of a minimal model. So the idea is this, the fundamental idea is this. If I know that something is going to be universal, for example, let me go back to this picture here. So let's suppose I know, for example, that the magnetization of a magnet or some complicated system is going to be universal. I've got reasons to believe that. And so you say, okay, fine, that's great, but I don't want to just know that it's universal. I want you to compute this particular function here, the solid line that goes through all these data. So you could say, well, I can easily do that. I can take a very detailed model of this material, CRBR3, whatever that means. Okay, so take that material, go to a materials scientist, learn about all the quantum chemistry of that, make a model of that, try to compute what happens for that material, and we can look at its behavior at a critical point. To do that with realism would be quite challenging to do, although I don't doubt that it could be done. But if you really wanted to know this curve here, and you had already been convinced that it was universal, you'd say you'd be an idiot to start off with the electronic structure and the quantum chemistry of this particular material, you'd be much better off starting with just a Heisenberg model and just computing with that, because the Hamiltonian is so much simpler. So then you have the idea then that what I can do is I can look at the simplest possible realization of the system and do my calculations on that, knowing that any more complicated model for the system I'm interested in would also give the same predictions. And so that's the idea, that we can use the normalization group thinking to make minimal models of emergence in real systems. So let me give you.
Can I ask a question real quick?
An example of that. Yes, somebody's on. Who's asking?
Adam.
Hi, Adam. Yeah, go ahead.
Can you go back a slide real quick?
Yes.
So you're talking about the defects and how you can have like local holes in order. If you're formulating your theory and you write the theory and everything, do those defects appear within the theory, or is it like in the real world experiment that you like try and form a crystal and then a hole appears? Or can you show in your theory that your theory predicts the order and the holes in the order?
That's right. It's the latter. The theory will predict what those holes can be. Now, something like a vacancy might be something that you say, well, that's an experimental detail. An atom was just missing there, and if you waited 1,000,000 years, that vacancy would diffuse out and go out through the boundaries of the material, and then you'd have a perfect crystal. So that's a true statement, and there's procedures you can do in an experiment to get rid of those things. You can do annealing, for example, to try to make your material have as few of those defects as possible. But these defects, the topological ones, those are intrinsic to the symmetry group of the system, and so when we describe the system, we will, by writing it down in terms of its degree of order, we will be able to predict what these things will be and how they will behave. And we'll be able to write down equations that describe the hydrodynamic, that's called the hydrodynamic description, the long wavelength behavior of materials. Again, that all comes from the theory.
Gotcha.
Yep.
Cool. Thanks.
All right, so here's the winners of the Nobel Prize in 2016. I'm sure most of you know these names: David Fowler, Mike Koslitz, Duncan Haldane. Anybody want to say what they noticed that is special or universal about these three people? This is not a scientific question so much, apart from the fact that they're all male.
Did they go from high energy physics into condensed matter physics?
I'm not sure. I don't know. David Fowler and Mike Koslitz definitely did. I don't remember if Duncan did as well.
They're all from UK.
They're all from the UK. Exactly right. Right. They're all from the UK, and they all have positions in United States universities. This was Margaret Thatcher's gift to American science. Anyway, so there's a lot of expatriate Brits in British universities and in American universities, including me, of course. And there's reasons for that that are not necessarily scientific. So that's right. So what did these people do? Well, I'm not going to talk about what Duncan did, but Koslitz and Fowler, I want to talk a little bit about what they did. So by the way, I should mention, David, I knew all these people, of course, personally. David Fowler, unfortunately, had passed away a few years ago. Random historical note, when I was on sabbatical in Cambridge, about 10 or 15 years ago, actually, I stayed in, my family rented his house. Mike Koslitz, I've known for a long time, is now works on non-equilibrium pattern formation and things like this, and that's how I came to know him for many years. All right, so what we're going to be talking about in the class is superfluids, and on the class website, you'll see that there's a movie page. And on that movie page, you'll see a wonderful movie that I digitized and posted on the internet with permission of the people who made the movie about the properties of superfluid helium. So roughly speaking, superfluids, honey is a normal fluid with viscosity at room temperature, so it flows, it's viscous and so on. Superfluid helium, roughly speaking, has no viscosity at say 1 degree above absolute zero. And we will talk in detail about whether this statement is really a true statement. It's not quite true. And we'll talk about what superfluidity really means. Now, the interesting thing is those are phenomena to do with real fluid mechanics. And yet what Constant Fowlers did was they made a model of the superfluidity literally based on the XY model, which is a model of spins in a plane. So the spins literally point in the XY direction only. They can live in 3 dimensions, so you have the dimensionality of the order parameter space, which is the XY plane, and you have the dimensionality of the physical space, which is X, Y, and Z, the real space. And we will be talking in detail about that distinction between order parameter space and the actual embedding space. So when we talk about spontaneous symmetry breaking, most of the time we're talking about breaking the symmetries in order parameter space, not breaking the space-time symmetries of the system. So this is what the XY model describes. It's basically arrows in a plane. We'll go through it in detail in the course. And one of the things that they predicted about the superfluid transition is this, that in 2 dimensions, the superfluid transition has a discontinuous jump. Even though it's a continuous transition, it has a discontinuous jump in the superfluid density at TC. I'll tell you how we quantify that when we get into details in the course. And that was predicted to scale in a particular way with the critical temperature. And these are data here. In fact, these are data from University of Illinois, from Jack Michel's group, and the data agree very, very well with the theory, with no adjustable parameter there. And this quantity, the superfluid density, turns out to be the emergent rigidity of a superfluid. Okay, so you may think of it as like a density, but the way that we'll learn to think about it is that what superfluid density really is telling you about is how stiff a superfluid is. And what do we mean by how stiff a superfluid is? What we mean is this: if I take the spins over here and the spins over here a distance apart, and I keep this one fixed and I bend this spin, I rotate its phase, how much does that bending of the phase raise the energy of the system? And the analog of the stiffness, or the Young's modulus, if you will, of a superfluid, is this superfluid density, and this was again something that came out of their theory. So this is a striking example of universality, looking at the simplest way that you can write down literally spins on the plane, or arrows on the plane, if you will. That tells you about the literally observables that you can measure in experiments in rather sophisticated superfluid phenomena. So the moral of this story is that very simple models can predict very complex phenomena. And going back to what we talked about last time, where we talked about the picture of emergence as being these successive levels of description, I would argue that in fact everything we know about the physical world comes from looking for simplest mathematical models that have the right symmetry and topology. And so I think everything that we know how to calculate and explain certainly in physical sciences and perhaps beyond, we really know that because we are always making models which are minimal models. And those minimal models have enough realism that they can predict what you're looking for, but on the other hand, they do not have excessive realism. Okay, so now I want to take a break. I want to talk about the purpose of doing computer simulation. So does anybody have any questions before I get into that?
I had a quick question.
Sure.
I think you said that the emergent states are characterized by a broken symmetry, or there could be a broken or a change in the topological order between the emergent state and the non-emergent state. Are there other higher order forms of order that could differentiate emergent from non-emergent states?
No, not that I know of. Now, it doesn't mean that they aren't, but I only know of those things.
Gotcha, gotcha. Thank you.
Yeah. You know, it's an interesting question. And what do you need to classify systems? I mean, I suppose, you know, I'm going to get on to non-equilibrium systems and living systems. I'm going to say a few things about that. And you might say, well, in those systems, there are other things that you can clearly see. So I would say I will kind of answer that question in a way when we talk about systems which are beyond these sort of simple physical equilibrium systems. Okay, let me talk about computer simulation. Okay, so what is the purpose of computer simulation? So this is a rant that I have, which was prompted by reading a passage in a collection of papers and essays by Leo Kadanoff, who was one of my mentors. And Leo Kadanoff, for those of you who don't know, was a condensed matter theorist. He was here at the University of Illinois. He worked on superfluids and superconductors and phase transitions and critical phenomena. He really invented this idea of block spins and looking at physical systems on different scales and different levels of description. And all of that was really the foundation for the renormalization group. In my opinion, he should have won the Nobel Prize along with Ken Wilson, and Ben Widham also should have been included in that, in my opinion. Now, one of the things that happened was Leo was here until the late 1960s, 1969. His most famous paper was written in 1966. And then he moved to Brown, and he decided to get into urban planning. Okay, now you might think, well, why is a theoretical condensed matter physicist doing urban planning? Well, you know, condensed matter physicists have broadened their interests into all sorts of areas. And today, it's not surprising that you'll see a condensed matter physicist who works on, you know, social phenomena or biological phenomena, you know, neural networks. There's many interdisciplinary applications. But at that time, that wasn't so much a trend, I would say. And Leo was always one of the trend leaders. So this is what he wrote. He said, at the time, there was a great national push towards understanding the dynamics of urban development. So we're talking about the United States in the 1960s, a period of great social unrest and you know, some changes were made, not enough, but anyway, he was interested in that. And somebody called Jay Forrester, who was at MIT, had developed a computer model of urban change, which took a very simplified view of an urban society, and then used the output of that model to prescribe social policy. I did not like the policy prescribed. This is Leo Kadanoff talking. So he says, I set out to use the same modeling tools that Forrester had developed to reach conclusions which were more to my liking. And our first result was that while not changing the model at all, we could reach opposite conclusions from that of the Forrester group. Okay, so here's an important point. Make a computer model. It may have excessive realism. There may be parameters that you can tweak, and it may be that as you tweak those parameters, the predictions completely change. They're not robust. So then he says, then we went on to build other models which more accurately recorded our own prejudices and points of view. And he's talking about his prejudices and points of view about the way society should be structured, and so on and so forth. And after a while, the point we had made began to sink in. If these models really represented little more than we could say in words, why not leave out the computer? In other words, what he was kind of saying, is partly this, garbage in, garbage out. You encode your prejudices in the computer, you run the computer simulation, it does what you already told it to do. So big surprise, what did you really learn? Nothing. And so he says, the construction of this sort of computer model seemed to me to be a rather pointless endeavor. For this reasons and others, I moved away from urban studies. And you can read this in this nice set of essays published about 20 years or so ago. And so then Kadanoff then moved to the University of Chicago and then became involved in the development in phase transitions, and then some time later in pattern formation and dynamical systems and so on. And that was the point where I got to know him. So the moral of this story is this. When you're doing computer simulation, there's two things you can do. You can use it to try to compute numbers that you can't compute analytically. So let's suppose I want to know what is the band gap of silicon. Okay, I can't compute that analytically. Well, at least I can't. Maybe there are people who can. So, but you can compute it by building very complicated models with excessive realism about the band structure and crystal structure and so on, and you could compute these things quite accurately with a sophisticated enough computer program. So you can get numerical information, literally a number in electron volts that verbal arguments cannot address. Okay, you can't argue verbally why the band gap should be one number or another. It's just something you have to calculate. You can argue verbally about why there should be a band gap. Should this thing be, an insulator or metal or semiconductor or whatever? That you can understand theoretically, but to get some precise numerical information, you need to use a computer to do that. So that's fine, and that's one good use of computers. The other thing you should do, though, is that you can use a computer to find emergent phenomena. An outcome of the dynamics that is not mandatory and usually collective, just as we've been talking about last time. So a question that you might want to ask is, what are the states of the system? What is the phase diagram of, say, a social system? What is the phase diagram of a superfluid, or a Mott insulator, or whatever it might be? That's a question that is a question about emergence and self-organization. And so the point about it being not mandatory means that when you find it in a computer simulation, it arose not because you put it in, but because it came out. Okay, you didn't dial it into the calculation, unlike what Kadanoff was doing here, where he was putting into the code his prejudices about how the system should behave, and then the system just did that. What you really want to do in computer simulation is not tell the system how to behave, and then see that it spontaneously develops some kind of collective phenomena that you're looking for. For example, herding behavior or swarm behavior in bees or insects or birds or fish or whatever it might be, or the onset of superfluidity in helium or something like that. So something that is emergent, that's what a computer is really good for. So in my own research, for example, I don't do this very, very much at all. You'll hardly find any papers of mine where I'm trying to find a detailed numerical calculation of a particular topic, or a particular physical quantity. What I'm usually interested in doing is using the computer to do experiments to find out what the phase diagram is and what are the important variables that control it. And that is, I think, how computers should be used. So again, we can exploit the idea of universality, the idea of minimal models, to build minimal computer models of phenomena and then see how we can use them. So let me give you some concrete examples of that. So let me give you one which is from one of my friends, Yoshi Ono, who retired from the University of Illinois recently, but was here for many years. And his early work was really quite remarkable. He was one of the first people to take the idea of mineral models and the normalization group in Universality and start applying it to real physical systems. So let's have a look at different levels of description of polymer systems. So here is a polymer as a chemist might view it. So there's some physical structure picture of a polymer, or this is a chemical formula structure of the monomers that are linked together to make a polymer. So that's an atomic level of description. Here is how one of my colleagues, also sadly passed away a few years ago, too early, Klaus Schulten, who was a pioneering computational biologist. So they would make models of proteins and other biological molecules, where you might say a large part of the molecule is some helix or some beta sheet or something like that, and then there might be some sites where there's some reactions occur or some important conformations that need to be captured, and so you would have a model of a polymer which is basically of elastic sheets with some multi-scale phenomena happening at the important loci. So that's a picture of a polymer from a computational biology perspective. This is how a theoretical physicist might view a polymer. The theoretical physicist says, well, atoms are round blobby things. And so if I want to understand the properties of matter made out of atoms, I should understand the collective behavior of round blobby things. If I'm a theoretical physicist and I want to understand the nature of polymers, I say polymer matter is made out of stuff that's long and stringy like spaghetti. And the question that I want to understand is, what properties of the matter follow just because it is made out of long stringy stuff rather than round blobby stuff? And we'll see that there are things that you can do like that. So each of these levels of description, it's not like that one is better than the other, but they answer different questions. So this level of description is what you are forced to use if you want to understand chemical bonding or reactions, things like that. This level of description is what you would use if you wanted to understand, say, protein folding or large-scale motions of a ribosome or the elasticity of a cellular membrane or something like this. And the spaghetti level of description is what you might want to use if you wanted to understand something like the thermodynamics of a polymer solution, or if I take polymers and stick them in solution in a fluid, how big are they? How do they float around? And so there's these different levels of description are good for answering different types of questions. So let's focus now on this spaghetti level of description, and let's just kind of ask, what kind of questions can we answer with that? So let's ask the simplest question that you can ask. So here's a picture of a polymer that I just sketched out. And you might ask the following question. The polymer is made out of monomers. The monomers have a length, little l. There's n monomers stuck together. So I've made a polymer whose total length, if all the monomers were laid out end to end, is something like this, L equals n times L. Okay, but in reality, these things are in solution, they're in thermal equilibrium, they are sort of floating around like this, and they adopt some conformation like so. And so the question you might want to ask is, how big is this polymer? So if you go and ask a chemist, so the chemist will say, okay, let me take the chemistry level of description, let me model the bond angles and the energy barriers to rotations about the carbon bonds, let me model the interactions with the solvent molecules, and so I'll make a very detailed chemical model of that, and then I will let it go into thermal equilibrium, and it'll sit there for a long time, sample many different configurations, and then I can measure the size from this big molecular dynamics or Monte Carlo simulation, and I can predict for you the size of the polymer in angstroms. Problem solved. Okay, so that works, and you can totally do that. The physicist might say, well, no, I'm not going to do that. I'm going to ask a different question. My interpretation of the question is this: if I know that I've got n steps, each of length L, how big is the polymer? To me means, how does the size scale as I change the number of steps? So let's think about what that question really means. Let's suppose I tell the chemist the polymer has 10,000 monomers strung together. And so they do that calculation. And then you say, oh no, actually I made a mistake. It's not 10,000 monomers linked together, it's 100,000. Okay, so then the chemist will say, fine, okay, I'll just put that into my computer. So they then make a bigger model and run it again and see what the size is. But the physicist will answer, no, I don't need to, all I need to know is how it scales. So the scaling is the kind of question that a physicist would ask. And what that means is, if I change the number of monomers, how does the size vary? Well, it's called the size R. If you just think of the polymer as being just a random walk in space, which is certainly what it looks like here, then the physicist will say, well, from Einstein's argument, which most of you have done in my statistical mechanics class, you will know that the R squared scales like n, and so the size scales as the length of the polymer to the 1/2 power. And so that's good. That says that if I tell you that n has increased by not 10,000 monomers but 100,000, I know I have to multiply the size by the square root of 10. Okay, so that's something that you didn't know, and that's good. As long as you know how big the polymer was at size with 10,000 monomers, I can predict how big it's going to be with 100,000 monomers. So that's the physicist's argument, and it sounds great, but it's wrong. Okay, and it's wrong because although this is a minimal model, a polymer is just a random walk, it is too simple. There's a famous quote from Einstein that says a theory should be as simple as possible, not simpler. And this theory is too simple. Why? Because it's left out an important qualitative feature. And that qualitative feature is that two atoms cannot occupy the same point in space. So a polymer is a spaghetti type object, but spaghetti can't go through itself. So because two atoms cannot occupy the same point in space, there are going to be some configurations where these trajectories, where the polymer chains actually go through each other. And then those configurations have to be removed. So if you remove those configurations from your ensemble of configurations when you do your averaging, then you're going to be left with only configurations that are bigger than that, configurations that don't include the crossing, configurations where they are void. And so therefore the polymer chain is going to be bigger than you would predict based on the random walk argument. So how much bigger? Well, again, you can work this out by renormalization group theory. And it turns out that the size doesn't scale as L to the 1/2, or L to the 0.5. It scales as L to the 0.588 with other decimal places. And this scaling is something that is independent of the chemical structure. It's true for DNA, it's true for polyethylene. Okay, it doesn't matter. It's universal, and it's asymptotically true for large chains. And in fact, as I take the L goes to infinity limit, the length going to infinity limit, that is like taking the limit as the temperature goes to the critical temperature in a phase transition. So in a sense, we can model the physical nature of a polymer chain by turning it into a field theory very close to its critical point. I'm not going to be talking about that so much in this course, but that's the way that one can do things. So this is again a nice way to answer the question. It tells you how the length scales, but of course it doesn't predict for you what the size of the polymer molecule is in angstroms. So you get two different answers to those questions, depending on what you're interested in. So here's another thing. We talked about the size just now. Remember earlier on we talked about the universal scaling near a phase transition. I showed you the magnetization data all falling onto one universal curve. So it turns out that suppose you ask this question, okay, I put polymer in solution. I have a concentration C of the polymer. What is going to be the osmotic pressure that you would measure? And you can calculate that by making a spaghetti model. And if you do that calculation, you measure the osmotic pressure pi as a function of over C over KT. And then on the horizontal axis is the concentration of the polymer, C, normalized in a particular way that the theory predicts. And then you get this curve here shown in black. This is a universal curve computed using a method in phase transitions in normalization group theory known as the epsilon expansion, which I teach in this class. And these data are data that were taken by Wiltzius et al. A year later from the theory. And you can see that without any adjustable parameters, without any material specific parameters, the data all fall onto one universal curve. So what this tells you is this: if you want to know what is the osmotic pressure of a polymer, you could either say, I want to know what that pressure is in pascals, or I want to know how it varies as a function of concentration. Doesn't matter what the nature of the polymer is, they will all fall onto a universal curve. And so that's the idea that one can use mineral models to make actual experimental predictions. So basically what I've told you is that the spaghetti model of a polymer is an example of a mineral model. It's flexible, a random walk, that's one model, it's too simple. You can make it a little bit more simple, a little bit more realistic by adding self-avoidance. But anything else that you add, at least for the questions that we're interested in asking as, say, a physicist or a physical chemist, anything else that you would add would be excessive realism, not necessary. So the model is good at answering some questions and lousy at answering other questions, like what is the size of the polymer in angstroms? Not a good way to answer those sorts of questions. So to a large extent, I think the success of physics is because we always tend to ask these sorts of questions, which are the ones that minimal models can be good at answering. And other fields, you might say, well, they're not as successful as physics. I would totally disagree with that. The questions that they're asking are much harder. So physics is successful to the extent that it is successful because it only asks simple questions. Okay, let me just very quickly give you some ideas about how that can be used for looking at pattern formation far from equilibrium. So one of the things that we will be talking about at the end of this class is the emergent order in systems far from equilibrium. And one of the things that systems far from equilibrium generically do is they form patterns in space and patterns in time. And the concepts that we're going to be using in this class, and we're going to be introducing, also apply to non-equilibrium systems. So the most amazing thing is this. I'm going to show you how one can describe systems like superconductors and superfluids. We will see that the same formalism applies also to the formation of patterns far from equilibrium. And we'll actually apply these techniques to study the formation of patterns in fluid convection at the end of the semester. So let's talk then just a little bit about a pattern formation. So here are some images. These are electron micrograms of what you would see if you took the chair that you're sitting on and then took the metal in the chair, in the legs of the chair or whatever, and put them under an electron microscope. And this is what you would see. And if you blew up this part over here, you would see something like this. Now, the thing that you should probably notice, if anybody here is a material scientist, let's say, or somebody who's been well trained, you would say, oh, these aren't very scientific pictures because, you know, the idiot professor has left out the scale bar. Anybody who's a scientist knows that when you show a picture, you should show the scale bar, right? Well, maybe, but the thing is this, we all know what the scale is, okay? We all know that this is basically microns, okay? So what we care about is not actually the scale, which is something, of course it's important in practice, but it's not what we care about for understanding the pattern. What we really are interested in is asking is, why do you get this shape? Why do you get these patterns in the first place? What scale it's on will depend on what is the material. For example, I can make snowflakes. These things here look like what you would see if you looked at the tip of a snowflake, something like it would be a different symmetry, but they'd look basically like this. These things are called dendrites. I can make dendrites on the scale of microns or smaller. I can make dendrites which are this big, okay, in a different kind of experiment, in a different setting. So the shape is the thing that is important. The dimensions is the thing that is not important. Now, it's important if you want to make your chair, you want to have the microstructure be literally microstructure. But in understanding the pattern, and the pattern is the thing that determines the mechanical structure, the thermal structure, the electrical structure, all the properties of the material, those really come from these shapes here. And these shapes, the morphology, if you will, which determine the physical properties, come from understanding the non-equilibrium dynamics that forms these materials in the first place. So now I want to show you how one can even apply these kinds of ideas to looking at dynamical systems, spatially extended dynamical systems. So let's ask ourselves the following question. How would we try to predict these very complex physical patterns using, say, a computer? So what you might say is, well, I know what the physics of this is. The physics is actually the flow of heat in the material, because when something turns from liquid to solid, it liberates latent heat, and that latent heat has to diffuse away in order to let the solid stay solid, otherwise it will remelt it. So you have heat diffusion. You have certain boundary conditions on the liquid-solid boundary interface, which I'm not going to go into. And so you could solve those equations on a computer, and you can indeed do that. Although at the time when I started working on this in the 1980s, it was impossible to do that, and one had to do other tricks that I'm not going to tell you about, but which one can do that. Okay, so typically the way you understand the physical properties of materials is you say, well, I can write down, say, the heat equation, some partial differential equation, and then to solve it numerically, what I have to do is I discretize it. So I put it onto some kind of lattice. I take the derivative, and I say the derivative is, u du by dx is just u at I plus 1 minus u of I over delta x. So I know how to translate a derivative into differences of the field values at different points in space. And then once I've solved my partial differential equation on a lattice, then I look at what happens when I make the lattice spacing smaller and smaller, and I check that my equations are grid converged and my predictions don't depend sensitively on my lattice spacing. So that, in a very, very crude nutshell, is what one does in numerical analysis of a partial differential equation. Partial differential equation is defined on the continuum. On a computer, I can only define variables discretely on a discrete lattice, and so I make such a lattice to make the lattice finer and finer and compute and solve the equations that I want to solve. That's the conventional approach. So we're not going to take that approach, and the reason is this. We're led by the idea of universality, emergence, minimal models, renormalization group theory. We're going to take this point of view. We're going to say, let's think about that. We start off by modeling nature as a partial differential equation. Okay, fine. Sometimes we can solve that, but usually we can't. So we have to put it on a computer. So now we discretize the differential equation. And when we discretize a differential equation, what we get are an infinite series, or finite in practice, but a large number of coupled maps that are coupled together, so the variables are all interconnected, and then we solve that coupled map and update it in time. And so that's literally what you're doing when you're solving a partial differential equation on a computer, like the Schrödinger equation, for example. So you might say, well, now that we've been attuned to this idea of universality and emergence, why not, if we're going to end up with a description that involves coupled maps, and we have this uncontrolled process of starting off with a model as a differential equation, discretizing it, making a set of coupled maps, and then solving a coupled map system, why don't we just forget about calculus altogether? Pretend it didn't exist. How would you describe matter if you didn't know calculus? Well, what you would do is you would just start off at this level of description. you would model nature as being coupled maps, and you would compute, and you wouldn't get anything, you wouldn't even start off with a differential equation. Okay, so, okay, fine, that sounds great in practice. Can you actually do that? So the answer is yes, you can, and I'm going to show you how. So the way that I want to give you an example of how one can do this. I'm going to show you what would happen with, say, a material science problem, the question of phase separation of an alloy. And then I'm going to show you what happens in a system which is like a liquid crystal, which has topological defects in it. I'm going to show you one can compute using minimal models, the normalization group inspired, and compute quantities that are very, very complex to predict. So this is an alloy made out of two materials, A and B. This is temperature. This is concentration of one of the alloys, let's say C. And then what happens is this: at high temperatures, A and B atoms are mixed uniformly in the alloy, and so they're uniformly dispersed in space. As I cool it down, the alloy will phase separate. So an example of a phase separation of an alloy would be salad dressing. French dressing, if you make a salad, you take oil and vinegar, you put them onto a salad. So what you do is you take oil and vinegar, you stir them up, you make a nice dressing, you pour it on the salad. Then you chat with your dinner companion, and while you do that, your salad dressing will phase separate. The oil and the vinegar don't like to be next to each other, and so they will form little globules of oil, little globules of vinegar, and if you talk too long, you will end up with some unappetizing mess on your salad, and you really won't want to eat it, okay? So what you want in salad is to be in this phase, but if you wait too long, you'll be in this phase. So this coexistence phase is something that will look like this. So let's think that orange and blue here is your salad dressing. And you can see that as I evolve it in time, I start off with something that's got little blobs in it. And as I wait longer and longer and longer, those blobs get bigger and bigger and bigger as these domains merge into one another. So that's just the dynamics of phase separation. And there's a process for this that's called, the material scientists would call spinodal decomposition. Now, why is it interesting? Why is it interesting to a physicist? Well, it's interesting for the following reason. If I take this picture here, and I cut out this little corner and blow that up, photographically enlarge it in Photoshop, I get this picture here. And if I just showed you this picture, and I showed you this picture, and I said, this picture on the left, this picture on the right, which one of these is the time evolution of this? And which one of these is just expanding the scale of this original picture? Well, unless you look very closely, you really wouldn't be able to tell. Okay, so then you can say, fine, let's take this picture, evolve it further forward in time, so I get this. If I took this little cutout of this one and expanded that, I would get this picture. And if I took the cutout of this one, which itself was the cutout of this one, and expanded it even further, I get this picture. So I get these three different pictures, all of which, up to pixel artifacts, look statistically indistinguishable. So what I've learned from this is that the time evolution is the same as changing the scale. And changing the scale is what I just told you happens when you're looking at critical phenomena. So you might say, aha, there must be some kind of scaling law here. And there is, and I'm going to show it to you in just a minute. Now, what we're interested in for this course is this is a system that has a scalar order parameter or a discrete symmetry. Either you're in the A atom or you're the B atom. Either you're spin up or you're spin down. High density, low density. So a discrete order parameter. And that discrete order parameter has boundaries between the up and the down regions, and that's the boundaries between the blue regions and the orange regions. When you have an order parameter that is not a scalar, but is a complex variable, so a complex number, or a vector, or an n-dimensional vector, or a tensor, then you have very different physics. That's what we're going to be talking about in the class. And you have topological defects and correlation functions. So I'm going to show you that in a minute. Okay, so let me show you that this picture, which you learned from this computer simulation, actually happens in real life. So, yes.
Sorry, we're like 6 minutes over on time, just a heads up. I don't know if you're...
Okay, I take it, I didn't realize that, but thank you for telling me. So because I've got full screen, so I can't see the time. I thought I was actually on time with 1 minute to go. But if we're over time, then I'm going to stop here and we'll carry on next time. So thanks for letting me know. So next time we'll talk about these dynamic scalings, and then we'll go on to some more complex systems. So thanks for the, well, you're right, we're 6 minutes over. Thank you. Great. Okay, so let me stop the recording.